Going back to the bet-alloc pattern from the beginning of this presentation, let's clearly illustrate how it happens by focusing on this CVE, which occurs in an open source project and was identified by the Cisco TEWAS team. The GPEG project on advanced content is a simple implementation of the MPEG-4 audio-video compression standard. In version 1.0.1, the library is vulnerable to decoding a specifically crafted MPEG-4 input file. The library code reads the number of entries value from a file into a 32-bit integer object, PTR-NB entries, and checks if it's not larger than the 64-bit input size, PTR size divided by 8. Unfortunately, this verification is insufficient as it doesn't check against the maximum integer size. This is a missing verify bug causing a DVR weakness. Next, the size of the memory to be allocated is calculated by multiplying the inconsistent number of entries value by the size of a U64 object, which can result in an integer overflow wraparound on a 32-bit platform. This is a wrong argument value TCM weakness. When such an overflowed integer is used, the allocation routine will create an undersized buffer, which will be populated based on its larger actual size by moving the pointer over bounds and using it to write there, aka buffer overflow. And this buffer overflow could lead to a denial of service or even remote code execution failure. To fix the bug, the GPEG team checked the maximum integer size, fixing the DVR bug, and resolving the entire vulnerability. Using the BF taxonomy of the involved weaknesses, first is the data verification weakness, DVR. The missing verification bug leads to inconsistent value for number of entries. The attributes show how and where this went wrong. Mechanism points the missing verification should have been checked against a range. Source code shows where the buggy code is in software. Execution space is about the permission level. State shows where the data is. Next is the TCM weakness. Wrong argument value to an arithmetic operator leads to integer overflow wraparound. The mechanism attribute here shows a multiplication operator is used to calculate the memory amount. The MAL weakness is wrong size used at allocation leads to not enough memory allocated for the buffer object. Its mechanism attribute shows how the allocation is done. The MET weakness is not enough memory allocated leads to pointer over bounds at repositioning. The mechanism attribute here shows how the pointer is being repositioned. Last in this vulnerability is the MAS weakness, which results in buffer overflow. The attributes are the same as for MET. The final error, buffer overflow, causes denial of service or remote code execution failure. Our next example is from a CWE. CWE 468, example 1, has a pointer scaling bug illustrating how a simple piece of code could have a bug and several weaknesses behind it. This is a common C++ pointer bug. It happens when a programmer miscalculates a pointer increment or decrement by a fraction of its type size. For example, when attempting to move an integer pointer 1 byte to the right. The chain starts with an improper casting of the pointer p to a char pointer that leads to invocation of a wrong addition operator that adds an int pointer n1 instead of a char pointer n1, miscalculating the number of bytes the pointer p should move to the right. Therefore, the pointer moves 4 bytes instead of 1 byte, 3 bytes off, and the code may end up reading or writing outside the object X, aka buffer overflow, or may have problems with the consequent allocation, delocation, or dereferencing. To fix the bug, the programmer should first cast and then add. Note that the C standard does not explicitly talk about overloading, but that required properties and equalities are met for overloaded operators. Using the BF taxonomy, the description of these 2 lines of code induced bug weaknesses chain is as follows. Our last example shows how BF is used to describe converging chains. Heartbleed was a serious vulnerability in the OpenSSL cryptographic software library. The bug was in the TLS implementation of the Heartbleed extension. The vulnerability was disclosed in April 2014 with the following CVE. The TLS and DTLS implementations of OpenSSL did not properly handle Heartbleed extension packets, which allowed remote attackers to obtain sensitive information from process memory via crafted packets that trigger a buffer overread, as demonstrated by reading private keys. For the lack of a more precise CWE, NVIDIA assigns it CWE 119, which covers both over and under bound and both reads and writes to from a buffer. But we can describe Heartbleed precisely with BF. Let's examine the code. The problem is in the data verification phase, where the semantics of the input should be checked and corrected. Payload is an unsigned integer and can be a huge number. It is input data that holds the payload length, but it's not checked towards an upper limit. Its value is not verified. This improper state is an instance of the BF data verification class, DVR. The operation verify is missing. Memcopy reads payload number of bytes from the object pointed by PL and copies them to the object pointed by BP. BP and PL are passed by reference by DST and CRS, and the huge payload length is passed by the argument N. First, 1 byte is read from PL and copied to BP. Then, until the huge payload length is reached, both pointers move 1 byte up, and the newly pointed by PL byte is read and copied. While BP is allocated large enough, PL points to an array with reasonable size. As the content of this array is read and copied to BP, so is also a huge amount of data from over its bounds. There are two improper states here, when PL gets repositioned over its upper bound and when data is read from there. The former is an instance of the BF memory addressing class, MET. There is no bug in the repositioning itself. However, a value that is inconsistent with the size of the PL object is used. The latter is an instance of the BF memory use class, MAS. Again, there is no bug in the read operation itself, but because PL points over bounds, the software reads data that should not be read, aka buffer overflow. This chain of BF states shows there is buffer overflow. However, it does not show how an exploit could reach sensitive information such as private keys. The missing size verification bug is not enough to get access to private data. There must have been another coding error due to which, unaware of the risks, an unused object with sensitive data is left in memory. To describe the bug in this parallel vulnerability, we use again the BF MAS class, but this time the improper operation is missing clear. Combining the final errors from both chains, the bugged software now can reach and expose sensitive information. The BF description of the Heartbleed vulnerability is: missing data verification leads to use of inconsistent size for an object, allowing a pointer reposition over bounds, which converging with missing clear allows reads of sensitive information and its exposure. Using the BF taxonomy of the involved weaknesses, first is the data verification weakness, DVR. The missing verification bug leads to inconsistent value for size of buffer. The attributes show how and where this went wrong. Mechanism points the missing verification should have been check against size. Source code shows where the buggy code is in software. Execution space is about the privilege level. State shows where the data is. Next is the MET weakness. Wrong size used at reposition leads to an overbounds pointer. The mechanism attribute here shows how the reposition is done. Last in this chain is the MAS weakness, which results in buffer overflow. Coming from another chain is again a MAS weakness. Missing clear leads to a non-cleared object. The attributes are the same as for MET. However, this is a different vulnerability and the source code is in different software. The final errors, buffer overflow and not cleared object combined, cause information exposure failure. The BF taxonomy and the BF vulnerabilities descriptions can be utilized in machine learning and artificial intelligence projects on software failures and risks. The BF classes are available in machine-readable formats, as well as the schemas for describing them, their bug and weakness instances, and the vulnerabilities that exploit them. The classes and all the possible values of operations, causes, consequences, and attributes are strictly defined. The BF vulnerability descriptions as chains of underlying bugs and weaknesses, each comprising of one operation, one cause, one consequence, and set of attributes, can also be generated in machine-readable formats. For example, this is the Heartbeat BF description. And this is the BAT-alloc BF description. In addition, all CWEs and BF class relations by operations and consequences are also available in machine-readable formats. This is actually the data from which we generate the CWE to BF digraphs by BF operations and by BF consequences. The machine-readable formats of the BF taxonomy, BF vulnerability descriptions, and CWEs to BF mappings can be utilized by machine learning and artificial intelligence projects on software failures and risks. The rich and well-defined sets of classes and possible values for operations, causes, consequences, and attributes, as well as any no alternative terms, can be used to query sets of BF vulnerabilities descriptions for natural language processing or to train ML algorithms. BF addresses a unique need. It has the support of vulnerability research teams such as the Crosset's team at JHU APL and Mirek Horley's team at RIT. Why BF matters? BF will allow precise communication about software bugs and weaknesses and will help identify exploit mitigation techniques. Government could improve the descriptions in public vulnerability repositories and create policies and guidelines for software testing. Software companies could improve the testing tools and their bug reports and implement automatic bug finding and fixing. Professors could teach better about bugs and weaknesses and conduct research on formalizing software bugs. All this will lead to improved communication about software vulnerabilities, increased precision in code review tools, and decreasing software bugs and weaknesses. Please do not hesitate to contact us with questions and ideas for collaboration.